Because the derivative of a function is a function itself, we can take the derivative of a derivative. The derivative of a first derivative is called a second derivative. We can find the second derivative of a function f by differentiating twice, denoted f double prime. Example 1 says find the second derivative of y equals x to the fifth power minus 4x cubed plus x to the negative first power. So in order to find the first derivative, we will use power rule a bunch of times. So we have 5x to the fourth power minus 12x squared minus x to the negative 2 power. So that is the first derivative, and then the second derivative, we would just take the derivative of that function and get 20x cubed minus 24x minus negative 2x to the negative 3 power. Let's just clean that up. So we get y double primed is 20x cubed minus 24x plus 2 over x cubed. Notice that there are two negatives here, so that becomes positive. And then I can make this negative exponent positive by putting it in the denominator. So that is our second derivative here. Part B wants us to find the second derivative of the function y equals the square root of x squared minus 3. And so notice that this is using the other notation rather than the prime or double prime. So dy dx is equal to, if we rewrite y as x squared minus 3 to the 1/2 power, then when we're taking the derivative, we can bring the power down and get x squared minus 3 to the negative 1/2 power. And then we need to make sure that we're using chain rule. So when we take the derivative of the inside function, that is 2x, and this 2 and this 2 should divide out. So we get dy dx equals x over the square root of x squared minus 3. So that is our first derivative. And then off to the side here, let's go ahead and calculate that second derivative. So d squared y over dx squared, that is the other notation for our second derivative. And we're going to need to use chain rule to take the derivative of this thing. We're going to need chain rule, but before that, we actually need quotient rule. So quotient rule, we have the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared, which removes the square root symbol. So let's see. This 2 and this 2 will divide out. We have the square root of x squared minus 3 minus x squared over the square root of x squared minus 3 there, all over x squared minus 3. If you'd like, you can do some further simplification by finding a common denominator between this and this, but leaving like this is fine as well. If you did end up simplifying it further algebraically, you would get that the second derivative simplifies down to negative 3 over x squared minus 3 to the 3/2 power like that. So if you want to maybe brush up on your algebra skills and see if you can simplify it down to that final answer, you can do that, but this is perfectly acceptable as well. Example 2 says find the first four derivatives of the function f of x equals negative 5x to the fourth power minus 3x squared plus 2x. So let's find the first derivative. That's going to be negative 20x cubed minus 6x plus 2. the second derivative, we would take the derivative of the first derivative. That's going to give us negative 60x squared minus 6. The third derivative would be f triple prime of x, and that's going to equal negative 120x. And then the fourth derivative would be negative 120. So there are the first four derivatives of that function. Example 3 says, let f of x equal 4x cubed plus 5x squared plus 1. Part A says, how fast is f of x changing at the ordered pair 1, 10? So in order to calculate the rate of change, we first need to take the derivative of our f function. So if we do that, we get 12x squared plus 10x. And then we need to evaluate f prime of 1. So that gives us 12 times 1 squared plus 10 times 1, which is 12 plus 10, and that equals 22. So to answer the question, the rate of change of f of x at 1, 10 is 22 y units per x unit. B says, how fast is f prime of x changing at 110? So in order to calculate the rate of change of the first derivative, we would need to calculate the second derivative, which is going to be 24x plus 10. And then we need to evaluate f double prime of 1. So we would plug in 1 to our second derivative. That would give us 24 plus 10, which is equal to 34. So that means that the rate of change of f prime of x at 1, 10 is 34, and then y units per x unit per x unit. Notice that we have this twice because it's the second derivative. Part C says, is f prime of x increasing or decreasing at 1, 10? Well, recall from the earlier example that f double prime of 1 is equal to 34, which is a positive number, and that indicates that f prime of x is increasing at 1, 10 because f double prime of 1 is positive. Okay, so example 4 is about acceleration, and these types of problems are very common amongst calculus examples or problems. And so usually you'll start out with s, which is called the position function. And then you have v, which is the velocity function. And then you'll have a, which is the acceleration function. And in order to go from the position function to the velocity function, you take the derivative, or you differentiate. And then same, if you want to start with the velocity function and go to the acceleration function, you would differentiate again, or take the derivative. So example 4 says, suppose that a particle travels according to the equation s equals 50t minus 16t squared plus 300, where s is the distance in feet and t is the time in seconds. Then ds dt is the velocity, and d squared s over dt squared is equal to dv dt. That's the acceleration of the particle. So the problem wants us to find the acceleration. So ds dt, which is the same thing as the velocity function, that equals 50 minus 32t, and then the acceleration function is going to equal the derivative of the velocity function, which is also the second derivative of the position function. And that just equals, so the derivative of the constant 50, that's going to be 0, and then the derivative of that part is going to be negative 32. And if you think about the units are going to be negative 32 feet per second, which is the same thing as negative 32 feet per second squared. And that is our acceleration for this example.